Good morning, all. Today we are going to discuss about software design patterns. Designing object-oriented software is hard, and designing reusable object-oriented software is even harder. So, software design patterns are used to design object-oriented software. And design patterns make it easier to reuse successful designs and architectures. And design patterns also help to choose design alternatives also. And design patterns can even improve the documentation and maintenance of existing systems. So what is a design pattern? So Christopher Alexander says each pattern describes a problem which occurs over and over again in our environment. And he also describes the core of the solution to that problem is that you can use the solution a million times over without ever doing it in the same way twice. So actually, Alexander was talking about patterns in buildings and towns, and what he says is true about object-oriented design patterns also. So our solutions are expressed in terms of objects and interfaces instead of physical structures like walls and doors. But at the core of both kinds of patterns is a solution to a problem in a context. In general, a pattern has four essential elements. The pattern name is a handle we can use to describe a design problem, its solutions, and consequences in a word or two. The problem describes when to apply the pattern. It also explains the problem and its context. It also describes specific design problems like how to represent algorithms as objects, like that. And it also describes class or object structures. Sometimes the problem will include the list of conditions also. The solution describes the elements that make up the design, their relationships, responsibilities, and collaborations. It does not describe a particular concrete design or implementation. The consequences are the results and trade-offs of applying the pattern. So model view controller. The model view controller triad of classes is used to build user interfaces. MVC consists of three kinds of objects. The model is the application object, view is its screen presentation, and controller defines the way the user interface reacts to user input. Before MVC, user interface designs tended to lump these objects together, but MVC decouples them to increase flexibility and reuse. So MVC decouples views and models by establishing a subscribe notify protocol between them. A view must ensure that its appearance reflects the state of the model. So whenever the model's data changes, the model notifies views that depend on it, and in response, each view gets an opportunity to update itself. And this approach lets you attach multiple views to a model to provide different presentations, and you can also create new views for a model without rewriting it. So a model communicates with its views when its value change, and the views communicate with the model to access these values. Another feature of MVC is that views can be nested. MVC supports nested views with the composite view class. It is a subclass of view. Composite view objects act just like view objects, and a composite view can be used wherever a view can be used, and it also contains and manages nested views. MVC also lets you change the way a view responds to user input without changing its visual representation. So MVC encapsulates the response mechanism in a controller object. There is a class hierarchy of controllers, and it makes easy to create a new controller as a variation on an existing one. A view uses an instance of a controller subclass to implement a particular response strategy. The view controller relationship uh, is an example of strategy pattern, and different algorithms or behaviors can be swapped easily. So there are three different types of design patterns: creational pattern, structural pattern, and behavioral pattern. In this video, we are going to discuss about creational patterns only. Creational design patterns. So they help make a system independent of how its objects are created, composed, and represented. A class creational pattern uses inheritance to vary the class that is instantiated, whereas an object creational pattern will delegate instantiation to another object. So there are two recurring themes in these patterns. First, they all encapsulate knowledge about which concrete classes the system uses. Second, they hide how instances of these classes are created and put together. All the system at large knows about the objects is their interfaces as defined by abstract classes. Then the creational patterns give you a lot of flexibility about how it's created, who created it, what gets created, and when. And it also lets you configure a system with product objects that vary widely in structure and functionality, and configuration can be static or dynamic. Sometimes creational patterns are competitors, at other times they are complementary. So first type is abstract factory. So the intent is to provide an interface to create families of related or dependent objects without specifying their concrete classes. So it is also called kit. So we can use the abstract factory pattern when a system should be independent of how its products are created, composed, and represented, or a system should be configured with one of multiple families of products, or a family of related product objects is designed to be used together and you need to enforce this constraint, or when you want to provide a class library of products and just you want to reveal their interfaces, not their implementations. Normally, a single instance of a concrete factory class is created at runtime. This concrete factory creates product objects having a particular implementation. So to create different product objects, clients should use a different concrete factory, and abstract factory differs creation of product objects to its concrete factory subclass. For this concrete product, it defines a product object to be created by the corresponding concrete factory. It also implements the abstract product interface. Client uses only interfaces declared by abstract factory and abstract product classes. Now the consequences. The abstract factory pattern has the following benefits and liabilities. First of all, it isolates concrete classes. That is, abstract factory pattern helps you control the classes of objects that an application creates. Because the factory encapsulates the responsibility and the process, it isolates clients from implementation classes. And it makes exchanging product families easy. That is, the class of a concrete factory appears only once in an application. That is where it is instantiated. This makes it easy to change the concrete factory an application uses. It also promotes consistency among products. So when product objects in a family are designed to work together, it's important that an application use objects from only one family at a time. So this makes this easy to enforce. And supporting new kinds of product is difficult. That is the only disadvantage. So extending abstract factories to produce new kinds of product is not easy. That's because abstract factory interfaces fix the set of products that can be created. So these are some useful techniques for implementing abstract factory pattern. So factories as singletons. So an application typically needs only one instance of a concrete factory. So it's usually best implemented as a singleton. So creating the products. Abstract factory only declares an interface for creating products. So it's up to concrete product subclasses to actually create them. The most common way to do this is to define a factory method for each product. Next is defining extensible factories. So abstract factory usually defines a different operation for each kind of product it can produce. So these kinds of products are encoded in the operation signatures, and adding a new kind of product requires changing the abstract factory interface, and all the classes depend on it. So a more flexible but less safe design is to add a parameter to operations that create objects. So uh, next is builder type. The intent of builder design pattern is to separate the construction of a complex object from its representation so that the same construction process can create different representations. So we can use the builder pattern when the algorithm for creating a complex object should be independent of the parts that make up the object and how they are assembled. And also the construction process must allow different representations for the object that is constructed. So the components of the builder patterns are, first of all, the builder. It specifies an abstract interface for creating parts. Then the concrete builder. It constructs and assembles part of the product by implementing the builder interface. It also defines and keeps track of the representations, and it also provides an interface to retrieve the product. Then the third one is director. It constructs an object using builder interface. The last product is product. It represents the complex object under construction. It also builds the product's internal representation and defines the process. It also includes classes that defines the constituent parts, including interfaces for assembling the parts for the final results. So the client creates the director object and configures it with the desired builder object, and director notifies the builder whenever a part of the product should be built, and builder handles requests from the director and add parts to the product. The client retrieves the product from the builder. That is the process. So the consequences are, it lets you vary a product's internal representation. That is, the builder object provides the director with an abstract interface for constructing the product. So the interface lets the builder hide the representation and internal structure of the product. It also hides how the product gets assembled. And it also isolates code for construction and representation. That is, the builder pattern improves modularity by encapsulating the way a complex object is constructed and represented, and it gives you fine control over the process. So unlike creational patterns, Builder pattern constructs the product step by step under the director's control. So typically there's an abstract builder class that defines an operation for each component that a director may ask to create. The operations do nothing by default. A concrete builder class overrides operations for components it is interested in creating. So there are some implementation issues to consider, like assembly and construction interface. So builders construct their products in step-by-step fashion, and builder class interface must be general to allow the construction of products for all kinds of concrete builders. And why no abstract class for products? So in the common case, products produced by the concrete builders differ so greatly in their representation that there is no gain from giving different products in a common parent class, because the client usually configures the director with a proper concrete builder. The client is in a position to know which concrete subclass of a builder is in use, and it also can handle its products. And empty methods as default in builder. So in C++, the build methods are intentionally not declared. So they are defined as empty methods. So it lets clients override only the operations they are interested in. Third type of design pattern is factory method. Intent of factory design pattern is to define an interface for creating an object, but let subclasses decide which class to instantiate. So factory method lets a class defer instantiation to subclasses. It is also called virtual constructor. So we can use the factory method pattern when a class cannot anticipate the class of objects it must create, or a class wants its subclasses to specify the objects it creates, or a class delegate responsibility to one of several helper subclasses, and you want to localize the knowledge of which helper subclass is the delegate. So the components of a factory method are product. It defines the interface of objects the factory method creates, and then concrete product implements the product interface. The creator declares the factory method, and it also defines a default implementation, and it returns a default concrete product object. You may call the factory method to create a product object. Then the concrete creator overrides the factory method to return an instance of a concrete product. So the creator relies on its subclasses to define the factory method so that it returns the instance of the appropriate concrete product. So there are factory methods eliminate the need to bind application specific classes into your code. The code only deals with the product interface. So we can work with any user defined concrete product classes. So a potential disadvantage of a factory method is that clients might have to subclass the creator class just to create a particular concrete product object. So subclassing is fine when the client has to subclass, but otherwise the client must deal with another point for this to subclass. So here are two additional consequences of the factory method pattern. So it provides hooks for subclasses. That is, creating objects inside a class with a factory method is always more flexible than creating an object directly. And factory method gives subclasses a hook for providing an extended version of an object. And it also connects parallel class hierarchies. Parallel class hierarchies result when a class delegates some of its responsibilities to a separate class. We have to consider these issues when applying the factory method pattern. First of all, the two main variations of factory method pattern are the case when creator class is an abstract class and does not provide an implementation, and second one, the case when the creator is a concrete class and it provides a default implementation. So first case requires subclasses to define an implementation. In the second case, concrete creator uses the factory method for flexibility. So it's following a rule that says create objects in a separate operation so that subclasses can override. So this rule ensures that we can change the class or objects their parent class instantiates if necessary. Then parameterized factory methods. So another variation on the pattern lets factory method create multiple kinds of products. So factory method takes a parameter that identifies the kind of object to create. Next is language specific variants and issues. So different languages lend themselves to other interesting variations. So you can avoid this by being careful to access products solely through accessor operations that create the product on demand. And we can also use templates to avoid subclassing. So this is a potential problem with factory methods, like they might force you to subclass just to create the appropriate product objects. So we can create a template subclass of creator that is parameterized by the product class. And there will be naming conventions. It's good practice to use naming conventions that make it clear to use factory methods. So fourth type is prototype pattern. Its intent is to specify the kinds of objects to create using a prototypical instance and create new objects by copying this prototype. So we can use the prototype pattern when a system should be independent of how its products are created, composed, and represented, and when the classes to instantiate are specified at runtime, and to avoid building a class hierarchy of factories that parallels the class hierarchy of products, and when instance of a class can have one of only a few different combinations of state. So the components are prototype. It declares an interface for cloning itself. Then concrete prototype. It implements an operation for cloning itself. Then client. It creates a new object by asking a prototype to clone itself. So here a client asks a prototype to clone itself. So the consequences are prototype has many of the same consequences that struct factory and builder have. It hides the concrete product classes from the client. So there are some additional benefits of the prototype pattern like adding and removing products at runtime. That is more flexible than other creational patterns because a client can install and remove prototypes at runtime. And highly dynamic systems lets you define new behavior through object composition by specifying values for an object variable. And many applications build objects from parts and subparts, and the prototype pattern supports this as well. And there will be reduced subclassing. That is, factory method often produce a hierarchy of creator classes, but the prototype pattern lets you clone a prototype instead of asking a factory method to make a new object. So subclasses can be reduced. So class objects already act like prototypes. And configuring an application with classes dynamically. Some runtime environments lets you load classes into an application dynamically. So the prototype pattern is the key to exploit such facilities. So prototype is particularly useful with static languages like C++, where classes are not objects, and it's less important in languages like Smalltalk or Objective-C. So we should consider the issues like this when implementing prototypes. So when the number of prototypes in a system is not fixed, keep a registry of available prototypes, and clients won't manage prototypes themselves, but they can store and retrieve them from the registry. So a client will ask the registry for a prototype before cloning it. So we call this registry a prototype manager. So implementing the clone operation means the hardest part of the prototype pattern is implementing the clone operation correctly. So it is particularly tricky when object structures contain some circular references. Then initializing clones. While some clients are perfectly happy with the clone, but others will want to initialize some or all its internal state to values. So generally, you can't pass these values, and we have to initialize the clones. So some prototypes might need multiple initialization parameters. So passing parameters in the clone operation precludes a uniform cloning interface. So you can also introduce an initialization operation. It takes initialization parameter as arguments and sets the clone internal state. So next type is singleton pattern. So the intent is to ensure a class only has one instance and it provides a global point of access to it. So we can use the singleton pattern when there must be exactly one instance of a class and it must be accessible to clients from a well-known global access point, and when the sole instance should be extensible by subclassing and clients should be able to use an extended instance without modifying their code. So the participants are singleton. So singleton defines an instance operation that lets clients access its unique instance. So instance is a class operation, that is a class method in Smalltalk and a static member function in C++, and it may be responsible for creating its own unique instance. So the clients access a singleton instance solely through singleton's instance operation. So the singleton pattern has several benefits. Controlled access to solved instance. Because the singleton class encapsulates its solved instance, it can have strict control over how and when clients access it. And the singleton pattern is an improvement over global variables. So it avoids polluting the namespace with global variables that store instances. And the singleton class may be subclassed, and it's easy to configure an application with an instance of this extended class, and you can configure the application with an instance of the class you need at runtime. The pattern makes it easy to change your mind and allow more than one instance of the singleton classes. That is, uh, you can use the same approach to control the number of instances, and only the operation that grants access needs to change. Another way to package a singleton's functionality is to use class operations. So the subclasses cannot override them polymorphically. It makes it more flexible than class operations. So these are implementation issues to consider when using singleton pattern. So singleton pattern makes the sol instance a normal instance, but the class is written so that only one instance can be created. So a common way to do this is to hide the operation that creates the instance. It guarantees only one instance is created. So this operation has access to the variable that holds the unique instance, and it ensures the variable is initialized. And this approach ensures that a singleton is created and initialized before its first use. And second thing, subclassing the singleton class. So the main issue is not so much defining the subclass, but installing its unique instance so that clients will be able to use it. So simplest technique is to determine which singleton you want to use in the singleton's instance operation. Another way to choose the subclass of singleton is to take the implementation and put it in the subclass. A more flexible approach uses registry of singletons. That is, instead of having instance, defines the set of possible singleton classes and name it in a well-known registry. So the registry maps between names and singletons, and registry looks up the corresponding singletons, returns it whenever needed.